The idea behind completing the square is pretty simple and fairly self-explanatory, really. If we have something of form x squared plus bx, and we want to be able to solve it, like if there was a 0 on the other side of there, if I was paying attention to my notation, well, what we could do is know that if we add in a b over 2 squared, then that would put us in the form of a perfect square binomial, x plus b over 2 quantity squared, where this trick, called completing the square, is really only particularly useful if x has a coefficient that is a perfect square, that is, if a is equal to 1 or 4, and really anything more than that, it becomes very ungainly. So really we just want x to have the coefficient 1, and then we want b to be even, because if it's odd, then we're talking about squaring a rational number. No one likes chasing that around. So really, completing the square, it's a nice trick, but it's got pretty limited uses, at least in terms of being efficient. Anyway, we're going to get an example here just so we can remind ourselves of how completing the square works. So for this, we want to complete the square to solve x squared plus 6x equals 2. Okay, so in this case, we do have a is equal to 1, and here b is equal to 6. Lucky us. Well prepared me. But anyway, what we're going to do is we're going to take that b value 6 and divide it by 2 to get 3. And that tells us, for this case, I know b looks like 6, not as well prepared as I gave myself credit for, but b over 2 squared ends up being 9, which looks even weirder now that I write that all out, but that's okay. You're getting used to my handwriting, hopefully. Anyway, that is our value that we're going to be wanting to add here, because if we add that in, we take x squared plus 6x plus 3 squared, just to be sure. That's a nice perfect square, but because we added 3 squared, we have to do it to the other side. Can't just bring in whatever we want, otherwise algebra wouldn't be very useful. However, it does give us something nice on this side. That whole thing just condenses down to be x plus 3, quantity squared, and then over here we have an 11. It's not perfect, but we'll have x plus 3 is equal to plus or minus root 11. Like I said, not perfect, but it is a number at the very least. So x is equal to negative 3 plus or minus root 11. And if we want to write that as a solution set, which I forgot to do in the last one, we would have the set negative 3 minus root 11, because we usually go ascending order, and negative 3 plus root 11. But the thing is, with completing the square, using the square root property, using factoring, getting to do that technically with some abuse of notation, you can get any of them to work for any quadratic, but sometimes it's just not worth the effort. And if you ever get into a situation where what you're dealing with just isn't worth the effort, it's just too clunky to get there, instead, what you can use is the fallback that people have been working on for 4,000 years, quadratic formula. And that's the next one we're going to get to.